Hi and welcome back. If you're new to the channel, my name is Vince. Thanks for stopping by. You're very welcome here indeed. So recently I interviewed Dr. Tom Stubbs. He's the CEO of a DNA methylation testing company called Chronomics. We spoke about a whole host of longevity flavoured subjects. There are timestamps in the description below. Enough waffling off me. Let's jump into the presentation and let's see what Dr. Tom Stubbs had to say.
Okay, hi Tom.
Hi Vince, great to meet you.
Sorry, that took a long time. First of all, thanks for taking time to do this. And can you please pass on my thanks to Anne, because she's been an absolute trouble. We're trying to get this tied together because you seem to be the busiest man in the world at the moment.
I will do.
So I've watched quite a few of your videos on YouTube, all very interesting. But for those who haven't, could you just go through a quick introduction to yourself and how you got into the epigenetics world?
Yeah, sure, happy to. So my background before founding Chronomics was originally in biochemistry at the University of Oxford, specialising in virology at the time, before heading over to University of Cambridge to work in the area of semiconductor physics applications of biology and directed evolution applications of biology, before then doing a PhD in epigenetics, particularly focused on DNA methylation, so understanding changes to our DNA that happen due to changes, for instance, in the environment and also with age, and developed a number of different methods for looking at that information, as well as predictors for age, and in particular kind of measures of biological age, so not how old we are, but how old we appear from a biological perspective. And that was really the genesis for the founding of Chronomics, with the mission as a company of making the unseen actionable, so taking biological information, making it visible and enabling downstream actions to happen from that, with the first product that we were bringing to market being a saliva-based test that captures that epigenetic information at the level of our DNA that is, unlike our genetic information, actionable and dynamic over time. And that has been kind of the I guess my journey from starting out to founding this company.
Excellent, great. So most of the viewers of my particular channel are more interested in just the measuring the epigenetic age to see that whatever things they're doing to try and reduce that number is actually working. So I know that Chronomics do that because you sell your product to donotage.org. What else do Chronomics do? Because I know they've got a much wider church, if you like, of epigenetics and health and longevity in the greater scheme of things. So what else do you do apart from age testing, and also what's your mission and what have you got planned for the future?
Yeah, sure. So our mission as a company, as Chronomics, is to, as I said, make the unseen actionable. So take biological information of many shapes and forms, enable it to be visible and enable downstream actions to happen from that information. We started out in the space of epigenomics and epigenetics because that was our background, our kind of core expertise from a global perspective. And we've now added to that and introduced a whole bunch of other data types, from looking at genomics, metabolomics. We've also launched, as of last year, Europe's first saliva-based test for detection of COVID-19. So looking at kind of virome-based readouts and information and immune system and immune health off the back of it. But very much our core focus from a foundation was that biological age readout, where epigenetics really is a gold standard for capturing the dynamics of the aging process at a biological level.
Okay, good. And I've had a couple of people who have, because I've said that do not age, do your epigenetic test, people have contacted me and said they'd like to come directly to you to purchase the test and to get onto your engine, if you like. But I believe you're just a B2B company now, is that correct?
So yeah, predominantly we work with partners, and the rationale for that being that as a company, we're focused on the biomarkers. So we're focused on delivering that visibility, that that information, making it accessible, but we want to work with partners that turn that information into something truly actionable.
Yes.
By delivering interventions. So for organizations such as Do Not Age to be able to get access to these biomarkers and then deliver solutions to support people living in the context, I guess, of Do Not Age, healthier and longer lives.
Great. So on the channel and videos that I post and comment on, we always talk about epigenetics and genetics. Can you just define exactly what the two are and what interactions they have with one another?
Yeah, sure, happy to. And I think, this is a quite a complicated one, especially on the epigenetic side. There's a bunch of different definitions out there, even within an academic context. But to take a kind of a fairly simple approach to it, your genetics is the information that you're getting from your mum and your dad that you're born with, and predominantly does not change throughout life. So the genetics you're born with are the same genetics you'll have if you're fortunate enough to live to 100 plus years of age. Importantly, there are a bunch of genetic conditions that people can suffer from that have very high penetrance. So if you have those genetic differences or variants or mutations within your DNA at birth, then you will have a visible condition or disease or phenotype. However, for the vast majority of things that people suffer from, things like heart disease, type 2 diabetes, other age-related conditions that we all know and are familiar with, very often the genetic component of that risk for that disease onset is very marginal. And actually, the far greater risk is that environment and lifestyle-related risk. So to take cardiovascular disease as an example, somebody could have a very high genetic risk for cardiovascular disease that puts them, let's say, 4 times more likely to develop cardiovascular disease than somebody at low risk, which sounds pretty terrifying until you consider how that risk changes when you take into consideration environment and lifestyle, where you start to see kind of 5,000-fold difference in risk. And when you look at it from that perspective, that genetic component is a small bit of that. When we talk about epigenetics and kind of how I would look at epigenetics, within the cells in your body, every single cell in your body pretty much has this genetic information that makes you unique and makes you kind of who you are. And that genetic information, if you stretched it out from any one cell in your body, is about 2 meters in length. And so obviously that is not how your cells handle that information. That information has to be carefully packaged and organized and constructed so that your cells can access the bits of that information they need in order to function and work and do what you need them to do in order to, stay alive and healthy. And that layer of packaging and control is epigenetics. So that is how your DNA is controlled and ultimately how it's accessed by the things in your cells, so things like proteins to translate or transcribe that information into RNA and then into proteins and to support you doing the things that you do. And importantly, it's that layer of information that the environment and lifestyle can alter. And obviously, as you age, it's that piece of information that kind of atrophies or struggles from an entropy perspective to keep up. And so that's the bit that's dynamic across environment and lifestyle and with age. And yeah, those are the two things, two distinctions, I guess. So one is your DNA that you get from birth, and the other is kind of how that information is controlled and how it's affected by environment and lifestyle.
You've actually answered the next question as well, because I was going to mention that I think it was 1 or 2 of the interviews you spoke in before where you mentioned that you could have a predisposed condition such as heart disease, but it's actually what you do in your life and the environment that has a much larger impact on whether that is actually going to affect you in years to come.
Yeah, 100%. So as I said, there are some conditions that are, high penetrance. So take trisomies. So something like Down syndrome. If you have that extra chromosome, you have the condition. but there's lots of genetic variations between all of us, as individuals, and these may kind of mean that we are slightly higher risk or slightly lower risk for something. But when it comes to age-related and chronic conditions, the vast majority of that risk, so for things like cancer, type 2 diabetes, heart disease, is driven in the vast majority of cases by environment and lifestyle-related components, not the genetics.
And that's borne out as well in a couple of studies I've looked at where identical twins have led two completely different lifestyles. And one has smoked and not used sunscreen and has stayed up late, hasn't had the right diet, the wrong kind of sleeping patterns. And physically, you can see straight away that they're not aging at the same rate.
Yeah, 100%. And you see that from the translation of the kind of epigenetic profiles as well over time. So when you have identical twins, the younger they are, the more similar their epigenetic profiles are, or epigenetic pictures are, if you look at them. And as they age, and obviously, as you say, they live lives on different trajectories, you see that gap widening over time, which is a reflection of that.
Yeah. Identical twins look a lot more similar the younger they are. As they get into their 20s, 30s, they start to become more like non-identical twins, if you like. There's something similar about them, but in some cases they are vastly different. Yeah. Part of the mission that you've got is to help prevent diseases taking place, or for people to have healthier lives, so they can prevent the things that are going to cause them to become sick or ill. How does epigenetics help with the preventative medicine side of things?
Yeah, sure. So one of the things that we're really excited about from a prevention perspective for epigenetics is what epigenetics really captures, and it's capturing long-term health trends or health risk, if you like, which is something that other biomarkers perhaps are capturing things over shorter windows of time. Epigenetics capturing over a wide window of time. And so, we're very good from a science perspective at defining biomarkers for disease or diagnostics. So there's, thousands, if not tens of thousands of those out there. But as defined by the World Health Organization, health is not just the absence of disease, it's the complete physical, mental, and social well-being of a person. Yeah. And epigenetics really gives you the ability to not just look at disease and define biomarkers of it, but actually capture health at a molecular level. And once you can start to do that, you can start taking a healthy population of people and looking at people that within that population are higher or lower risk for things because of their environments, how they're living their lives, etc. And so you can support people with the avoidance of those age-related and chronic conditions rather than just measuring the diseases when they've already appeared. So that's something where I think epigenetics is really uniquely placed to support.
It's interesting. It was a question I was going to ask later, but I think it's more relevant now. I've had some awkward conversations with health practitioners about the journey I'm on with taking NMN and resveratrol and other age-related or age-reducing supplements. If people use your information and they gather all of this biological data, do you think there's going to be any pushback, or do you think that doctors are going to find this difficult to adapt to when a patient comes in and says, this is what I think is wrong with me because looking at all the data, this is what's happening to my body. And when we spoke a year ago, you told me to take this course of action and nothing's changed because all my biological data is exactly the same. How do you think the medical profession are going to react to this?
Yeah, sure. Well, I think in general, there's a transition happening within health, within medicine right now, and it's being sort of accentuated, I guess, by the current pandemic, by COVID. But a transition that's been there in the background for a while of going from generalist and reactive medicine or healthcare to much more personalized and proactive or preventative health management. And very much as part of that journey is each of us as individuals becoming much more informed about our health. Yes. This information is becoming more democratized. Like that's kind of one of the core things that we as a company want to do as well, is to democratize access to biomarkers, because there's no reason anyone on the planet can't understand their own health,
Yes.
at the level of this kind of information. Will doctors in the first instance, all of them kind of appreciate people being informed with this information and coming to them with it? We have many examples of where doctors do, and they actually, really embrace the fact that people that they're there to support are trying to support themselves as well. But as with any change, there's always going to be people that are kind of dragging their heels and not wanting to transition into that movement, and also aren't so comfortable with not being the one holding all the cards, all the information. But I think one of the really exciting things of enabling people with this information and giving this information to people is that, yes, stuff that on the whole is good for people that we've been doing for decades may not work for certain individuals and may be great for other individuals. But it's giving, doctors and individuals the opportunity to understand what's going to work for them. And it's only by giving people these personalized insights and putting them into contexts of risk models and what makes sense for any given individual that we'll be able to transition to a preventative world.
I think we're definitely at the cusp of something that's very interesting for the future. I think the notion that homeostasis and everybody's roughly the same, and if you don't fit in, then there's something wrong with you, and we have to treat it, I think is changing, where people are different, and there should be different forms of treatment and medication for people who have different needs, if you like.
Yeah, 100%. And this was, taking a kind of, very different perspective, but from an engineer's perspective, with the US Air Force, decades ago, there was a realization that when they were first kind of designing fighter jets for the pilot seat, taking average measurements across all pilots to define how that seat should be and where the control should be and stuff, and realizing that, they were having crashes off the back of the fact that there was no average person. Everyone had things that meant that nothing was right when you took the complete average. And I think that's also true in health. No one is utterly normal or average. We're all a bit weird in our own little ways. And these nuances, it's right that we should let them kind of come to light and embrace the individuality of people and not kind of force us all to conform from a health perspective when actually, that's not necessarily right for everyone.
Yeah, I think it's far more, you take more responsibility when you can be more proactive with the outcome of your health. You take more responsibility, as opposed to being able to go to the doctor and say, treat me for what's wrong. And if the doctor can't put it right, then you can kind of put some of the blame on them. If you use all the systems that are now available and you take responsibility and you're more proactive, I think it's far better for everybody.
Yeah, sure. And I think part of this is also, with these biomarkers, you're now giving people access to information where they can see that something, although they're healthy, isn't right or could be done better. Because you're right, as you say, people wait until something's wrong, typically, to seek help. And what you're allowing with these biomarkers is to say, okay, nothing is wrong, but stuff could be better, and kind of here's the visualization of that. So go and act. So you're priming and enabling people to act from a much earlier point in the health trajectory or illness trajectory than was possible in the past.
That's the thing I think is very, very interesting, exciting actually. So the just getting back to the epigenetic age test, you measure 20 million markers, individual markers?
Yes, we look at, from an epigenetic sequencing perspective, we're looking about a sixth of the genome, within which you've got millions of cytosines, which are the kind of particular, so in your DNA, you've got kind of 4 letters, A, T, C, and G, and C letter or cytosine being where methylation, or these chemical tags that we call DNA methylation, that are an epigenetic tag or mark, can be found. And so we're measuring millions of those across a sixth of the genome. So
how, and I know you don't want to throw shade on any other company, but other companies already, or I say only, but measure maybe 100,000 or 250,000 markers. What do you think is the difference in what's the margin of error with the millions that you do and the hundreds of thousands that they do with regard to giving someone's biological age?
Yeah, sure. So, well, I think there's a couple of differences, and there's some really fundamental differences between the different underlying tech stacks that these different things are using. So you have some people out there measuring biological age with handfuls of positions or hundreds of positions using amplicon or PCR-based approaches. And when you're dealing with that, you have challenges around your ability to account for underlying reasons why that could happen. So for instance, we as a company specialize in particularly getting this information from saliva, but if you're looking, for instance, at blood, people's blood cell counts change pretty predictably as people age. And so if you don't correct for those sorts of things, which is pretty difficult to do if you're looking at only a small number of positions, you're not really capturing somebody's biological age as measured from kind of, what's happening within their cells intrinsically, but you're capturing the changes to the immune system, which is something quite different. If you're looking at hundreds of thousands of positions, you're probably using kind of methylation array type technology. You have the ability to correct from a cell count perspective, and you can get kind of really robust measures of epigenetic age. But there's also, again, kind of lots of things that you can't do from understanding how the dynamics of your age are changing kind of within a strand or kind of within certain DNA contexts. And you also don't get access to other types of information that could be impacting age. So for instance, it's a lot more challenging to remove genetics having an impact on those epigenetic signals. And then when you're looking at kind of millions of marks, you're predominantly looking at a sequencing-based technology, next generation sequencing. And if you're looking at that, then you have an understanding of allelic methylation, so methylation coming from your mum and coming from your dad. You have an understanding of underlying genetic variants that could be impacting those methylation profiles. You have the ability to correct. You also then have, obviously, the ability to define really robust and accurate biomarkers for things like biological age as well. And you're capturing much more of the genome. So it gives you a better understanding of how aging is playing out across a far greater kind of overarching context across your whole DNA than you would from an array where you're sampling little pieces of it.
So where do you think methylation testing measures up against telomere length testing? Because that's another in vogue kind of biological age test now is the length of your telomeres. Do you think they're comparable or not?
So if you're looking from an accuracy perspective, if you're looking from a kind of indicative of the aging process perspective, etc., epigenetic age stands out far above a telomere length measure. So for instance, from telomeres being long can be due to a number of different reasons. So for instance, you could have long telomeres because you've developed a type of cancer that reactivates telomerase. And so you have long telomeres, which would be indicative of looking young, but actually, from an age-related perspective, that's pretty damning. It's also telomeres in general, just fundamentally as a biological concept, telomere aging is not something that happens across species. So if you look at, for instance, mice, you can essentially have mice where there's no telomerase, so no ability to keep your telomeres long from generation to generation, and those mice are absolutely fine for a number of generations. If you did that in humans, it would be a completely different story, but the point is it's not something that's evolutionarily conserved. Okay. If you take epigenetic age, and we did this back when I was working in an academic context, you can define epigenetic age predictors across a whole range of different species, from mice to dogs, so kind of pets to humans to whales to that system holds across different lifespans. Obviously, you're talking about mice, you're talking about a couple of years kind of lifespan up to kind of human, or whales. Different types of whales have different lifespans, etc. And you're able to capture epigenetic age across those different species in a way that, from a telomere perspective, you wouldn't be able to do. It wouldn't be meaningful within different species necessarily.